So again, we are doing all the necessary preparations so we can start talking about infinite series. And the first step is to discuss these notional sequences. We started doing this last time. We talked about what it means for a sequence to converge and to diverge, which basically means where the limit exists or not. And now we're just gonna get a couple more tools to be able to determine whether the sequence converges or not without actually having to compute the limit. Because sometimes this is pretty difficult. Okay. Okay. So for this, we need a couple of definitions, which is basically very straightforward. The notion of monotonic sequence, and by monotonic I mean either increasing or decreasing. Remember, sequences are functions. Okay. An increasing function is a function that's going on, right? Same thing with a sequence. The sequence is increasing if its terms are getting bigger and bigger. Okay. And similarly with decreasing. So let me define this. So sequence AN, okay, is said to be monotonic, non-decreasing, and then in parentheses, I'm gonna put monotonic non-decreasing, so I'm gonna put in parentheses increasing, and I will explain why. It's technically not the same thing, okay? Because when I say non-decreasing, what I mean is it doesn't go down, but it will stay the same, okay? If you say increasing, it means it doesn't stay the same. It's always going up, okay? So there is a slight difference. So it's said to be monotonic non-decreasing if I would say here monotonic non-decreasing for n greater than or equal than n0 if for all n greater than or equal than n0 we have that the an term is going to be that the an plus 1 term is actually greater than or equal than an. Let me write it. There we are. An is less than or equal than an plus 1. Okay. So basically, non-decreasing means, and the reason why I put this n0 here is just to say at the beginning, the terms of the sequence may be behaving a little bit weird, but then if after one point the terms they organize in such a way that they start getting bigger and bigger and bigger, then that's what I'm saying here. Okay. So probably at the beginning you have a few terms that is going up, then it's going down, up again, and so on. But if it eventually stabilizes and start behaving this way, it's still monotonic. You just ignore the first few terms. Okay. So it's non-decreasing if for every term in the sequence, starting at a given point, the nth term is less than or equal than the n plus 1. Okay. So the next term is always bigger or equal to, and the next one is bigger or equal to, and so on. So it's either staying the same or going on. If you want to say that it's increasing, we just put on a straight inequality. So the increasing situation is an less than an plus 1. So what's in parentheses is the blue definition. It's said to be increasing if for all n greater than or equal than n0, an is less than an plus 1. If you want the non-decreasing, then you look at the right definition. Okay? Just put in two definitions in one. So again, it basically just means that the terms of the sequence keep getting bigger and bigger as you go deep into a sequence. Okay, that's all. And then similarly, monotonic non-increasing or decreasing is if the terms keep getting smaller as you go deeper into the sequence. So sequence AN is said to be monotonic non-increasing, and then alternatively you could say decreasing, but then of course decreasing means that it's always getting smaller, so you don't allow the sequence to have terms that are equal to each other. Monotonic non-increasing, and once again for n greater than or equal than n0, if for every other n, if for all n greater than or equal than n0, we have that an is actually greater than or equal to an plus 1. So as you get deeper into the sequence, your terms are getting smaller and smaller. Okay, that's basically what we're saying. And if you want to say decreasing, then that's just a straight inequality. Okay. And then if a sequence is either increasing or decreasing, and when I say increasing, let's make the agreement that when I say increasing, I probably really just mean non-decreasing. Okay, so we just be putting, unless I really want to stress that it's a strict inequality. When I use the word increasing, if you see me writing the less than or equal to, then I really am saying non-decreasing, because that is painful to be saying non-decreasing. Right? It's easier to say increasing.
It sounds redundant, but it's not.
But you see, it's this little quality that you have to be careful. But as long as we agree, when I say increasing, what I'm saying, then we're fine. Okay, so if it's either increasing or decreasing, so one of the two cases, we say the sequence is monotone. Okay, the sequence is monotone if it's one of the two. If you want to stress it, then you say monotonic, increasing or decreasing. Okay, so the sequence that is either one or two from above is said to be monotone. Okay. All right. So let me give you some examples. I'm going to give you some sequences, and let's decide whether they are monotonic or not. Okay. All right. So examples. And let's see. First one. So determine if the sequence is monotone, and if so, classify. Oh, let me just say this. Sequence is monotone. All right, so let's do number one.
What makes something monotonic?
So monotone, monotonic. So again, monotone, monotonic is the same thing. It's,
right.
But then monotonic, non-decreasing. I mean, that's the definition. It means you're gonna see in the examples. So non-decreasing means as you get deeper into a sequence, your terms are never getting lower. They either stay the same or they go up. And non-increasing means as you go deeper into a sequence, your terms don't go up. They stay the same or go down. Right. Okay.
So as long as they continue to consider monotone.
You will see. We're gonna do examples now, so this concept should sink in once we do the example. I mean, the key here is this. This is the definition. For all n, this happens, so that means decreasing. Your terms are going down. When for all n, that happens, that means increasing. Your terms are going up. That's what you care about. All right. So let's say a sequence with general term 2 plus -1 to the n. What do you think? Is this monotone?
No.
Why?
Because it just goes up and down to.
It keeps going back and forth, right?
Right, yeah.
So remember, this sequence here, what is this sequence? So let's see, when, it doesn't matter, we want to start at 0 or 1. Let's say it's the,
Oh, I'm sorry, 3 to 1.
it doesn't really matter, but okay, I'm gonna start at 0, so I'm gonna put this sequence at 0, starting at 0. So when you start at 0, then that means the first term is 3. Then what's the next one? It's gonna be a 1, then a 3, then a 1, 3, and 1. Keeps going this way, right? When n is even, you get 3. When n is odd, you get 1. So it's not monotonic because no matter what term you are, when you look at the next one, it goes up, but then the next one goes down. So it's going up and down, up and down.
So it's not consistent.
Exactly. It doesn't exhibit this consistent behavior of always going up or always going down. Okay? So it's not monotonic. So let me justify this. So an is not monotonic. Non-increasing because, so to justify this, we just need to show that it actually goes up because let's say a1 is equal to 1 and a2 which is less than a2 which equals 3. Okay, so it does go up, so it's not monotonic, not increasing. And this actually happens, deeper into a sequence. And similarly, we can say that this sequence is not monotonic, non-decreasing, because it does go down. For example, we can say, look, A2 is equal to 3, and then it went down because A3 is equal to 1. Okay? So here it went up, and then here it went down. So it is not monotonic, non-increasing, and also it fails to be non-decreasing. So non-monotonic. Do you understand this? All right, so let's take a look at another one. How about the sequence Bn given by 2n over 1 plus n? So here you kind of should have an intuition of what's going on. So for example, the top is twice n, the bottom is just n plus 1. So it kind of makes sense to think that, first of all, the bigger n is, the bigger will be this number, and moreover, the bigger n is, the bigger 2n is going to be when you compare it with 1 plus n. So it makes sense to think that this fraction is going to be getting bigger and bigger as n goes big. But we need to argue this. It's not something that, it makes sense. We have to argue, okay? So, but you need to know what is it that you're trying to argue. So claim, actually, let me not put any claim, because what if you don't have the intuition? I'm going to show you different ways that you can actually show monotonicity. So note, what we really want to do is we want to compare Bn and Bn plus 1, right? This is what we really want to do. So if we say that Bn is less than or equal than Bn plus 1, this is equivalent to say the following. It's equivalent to ask this question, Bn plus 1 minus Bn greater than or equal than 0. Okay? So basically what I'm saying is to say that something is bigger than something else is equivalent to consider their difference and show that the difference is positive, right? If you look at the difference of these two terms, if this is positive, that means the first guy is big. If this is negative, then the first guy is smaller. Do you understand this? So if we can show this inequality for every n, then that means that the terms are getting bigger and bigger. And then you get that is monotonic, non-decreasing. And if you argue that you can actually put strict inequality of the time, then it will be increased. Okay? So let's try this. This is just using basic algebra. Then, of course, you can use more advanced techniques, because sometimes the basic algebra doesn't really help, and then you will need to use Car 1. Because you can look at the function corresponding to the sequence and then take derivative. Because the sequence is increasing, it's the same thing as saying that the corresponding function is increasing. And as you know, if the derivative is positive, the function is increasing. If the derivative is negative, the function is decreasing. Okay? But you can leave that for cases in which simple algebra doesn't do the job. Here, the simple algebra should be enough. All right, so to figure this out, what we're going to do is we're going to work here. Okay? Because it's easier. So let's consider Bn plus 1 minus Bn. What is this equal to? Bn plus 1 just means go to the formula and replace n by n plus 1. So that's 2 times n plus 1 over 1 plus n plus 1. Okay? Oh, by the way, this sequence is for n, let's say, greater than or equal than 0. Okay? It's okay for n to be 0. All right, and then minus Bn. Bn is just 2n over 1 plus n. And let's calculate this, and let's see what we get. So this would be 2n plus 2 over n plus 2 minus 2n over 1 plus n. So Bn plus 2, 1 plus n, so you get 2n plus 2 times 1 plus n minus 2n times n plus 2. And clear denominators and all of that business. So we get, clear parentheses. So 2n plus 2n squared plus 2 plus 2n minus 2n squared minus 4n over this n plus 2 times n plus 1. So what do we get here? This guy cancels with this one. and then these two n's will give you 4n, which cancel with this one. Okay. So on top, the only thing that survives is a 2. So we get 2 over n plus 2 times n plus 1. And then the question that we are asking is, how does this fraction compare to 0, right? Well, you know, it really depends on the top and the bottom. The top is always positive. The question is, what about the bottom? Well, our n are 0 or bigger, right? N is just a counter for the terms in the sequence. So this denominator is also positive. So this fraction is always greater than 0. Yes? Because this fraction is always greater than 0, what this is telling me is that bn plus 1 minus bn is always greater than 0. So bn plus 1 minus bn is always bigger than 0. Which, of course, is equivalent to say that bn plus 1 is bigger than bn, and this happens for all n. Right? So what can we conclude about this sequence? Is it increasing or decreasing? Is increasing. So this is monotonic increasing because as you go deeper into the sequence, your terms are getting bigger and bigger. The next term is bigger than the previous one. The next one is bigger than the previous one. So, okay. If you would have gotten that this is less than 0, then it would be decreasing because that means that the next term is smaller than the first one, right? If the difference of two numbers is negative, that means the first guy is smaller than the second guy. So the sequence Bn is monotonic, increasing. You could say monotonic, non-decreasing, but increasing is stronger because it's actually greater than 0. Yes?
Could you find the derivative of 2n over 1 plus n? Because that would have been the slope of 2n plus over 1 plus n. And if it's positive, wouldn't that mean it's increasing?
Yeah, like I said, you can use calculus. You can look at not the derivative of 2n over 1 plus n. You need to look at the function. This is not, these are dots. So what do you mean by derivative? Now, you can look at the function 2x over x plus 1 and do the derivative of that.
Yeah, that's right.
Okay, yeah, I know. And just
replace
clarify.
Replace n with x.
Yeah. So you take the derivative of that function, and if you can argue that the derivative is positive, that means your function is going up. Yeah. And sometimes that's what we need to do, because sometimes, you know, here all we did was subtract the two fractions, and then that's it. It's pretty simple. It's just algebra. But sometimes this doesn't really tell you much, and then you have to use other techniques. Okay. Let's see an example now. All right. So how about this one? Let's say Cn is going to be a sequence given by n squared over 2n minus 1. Okay. And let's say that this is for n greater than 0, so greater than or equal than 1. Okay, so again, here, I don't really, if we try to do the algebra, it's going to be, it could get a little bit ugly rather quickly. But let's go ahead and let's try to list some elements, because it's always good to list some elements. Okay, we actually looked at this sequence before, last time. So this sequence, let's see what are the first few terms. So when n is equal to 1, what do we get? We get 1, right? When n is equal to 2, what do we have? So we're going to have 4 over 3. So what just happened here? So notice that this is C1. So C1 is equal to 1 is smaller than C2. So our sequence just went up, right? Mm-hmm. Now, if we want this from the beginning to be increasing, let's say like the previous sequence, we better get the next term to keep going up. If our next term goes down, for example, then we lose monotonicity. But then a good question would be, do we actually gain monotonicity at some point? Because at the beginning it could be behaving up and down, but then eventually it goes nice. Because the motivation, I mean, the idea is that it should be decreasing. Why? Because when at the beginning, n squared could be bigger than 2 to the n. But at some point, this exponential is faster than this one. So this is going to win, right? So eventually, the denominator here is going to be way bigger than the top, and then this has to start getting smaller and smaller. you know, the limit is 0 for this. Exponential, it goes faster than quadratic. But the question is, when does this start to happen? That the sequence starts to go down, okay? So that's what we will try to investigate. And we will need calculus for that. All right, anyways, let's take a look at the next one. What's the next term? So it'll be n equals 3. So we get 9/7. So what just happened there was 9 divided by 7. How does that compare with 4/3? So you multiply this by 7, you get a 28. You multiply this by 3, you're going to get a 27. 28/7 is bigger than 28/21 is bigger than 27/21, right? So this number is bigger than this one. So it now went down. Okay? So 4/3 is bigger than 9/7. So it went down. So notice at the beginning that the sequence shot up, then it went down. Now the question is, does it keep going down or does it come back up again? Let's find a few more terms and see what happens. So let's see, when it's equal to 4, what do we have? 16/15. How does that compare with 9/7? How does this compare with 9/7?
It's smaller.
Smaller?
Mm-hmm.
Yeah? Okay. Are we sure?
1/15 is smaller than 1/7.
Huh?
Isn't it smaller?
Well, maybe.
Yeah, because 1/15 is smaller than 1/2/7.
Right. Good. 1/15. Yeah, good. That's one way. Yeah. 1/15 and then 1/7. Yes, agree. So it went smaller. So it went down now. So the question is, does it keep going down? Let's try to investigate because, you know, maybe how do you know that at the 20th element it doesn't go back up? Right. Okay. So let's do some calculus now. So first of all, we can see that because of this, we can see that it's not monotonic, right? Not monotonic for n greater than or equal than 1. But now the question is, at least we see now that starting at 3, actually, if you want, starting at 2, it seems that the terms are going down. Does this keeps happening? Let's try to investigate this. Okay? So, question. Is it decreasing for n greater than or equal than 2? In other words, if we know the first term, can we then say that it's decreasing? Okay, so let's see. It certainly seems that it is starting to behave that way, but let's try to see. So for that, I'm not going to even try algebra because, again, that exponential is not going to really help us much. So I'm going to go straight to calculus. Okay, so I'm going to consider the corresponding function, that's x squared over 2 to the x minus 1. And then let's find the derivative, and then what we want to argue is that this derivative for x greater than or equal than 2 is going to be negative. Okay, that's what we want to argue. Because negative derivative means the function is decreasing. All right, so to take the derivative, we have to use the quotient rule, right? So remember, derivative of the top times the bottom minus the top times derivative of the bottom. That's 2 to the x times ln of 2 divided by the bottom square. And remember, we are analyzing this function for x greater than or equal than 2. Okay? All right, so to analyze the sign of this derivative, you know, this is a fraction, so it depends on the top and bottom, but the bottom is always positive because we have this square. So the sign of this depends really on the top. So let's focus on the quantity that we have on the top. Let's clean this up a little bit. I'm going to factor out 2 to the x, and actually, yeah, I'm going to factor out 2 to the x, and then I cannot factor out 2 to the x. I just clear parentheses. So that will be x times 2 to the x plus 1 minus 2x minus x squared times 2 to the x times ln of 2.
Oh wait, is that minus 1 part of the exponent?
Huh? Which
Why do you put a plus one in the 2 to the x?
Oh, because when you do 2 times 2 to the x, that's 2 to the x plus 1. And distribute clear in parentheses.
Okay,
Right?
right.
All right, so let's see, what can we do here? There is this x that I can take out for sure. But then let me try this. And I'm just gonna take that numerator and then play with that. Okay, so I'm gonna take this. Let's go ahead and let's factor out. So we have x times 2 to the x plus 1 minus 2 to the x minus x squared times 2 to the x ln of 2. So I'm gonna factor out x times 2 to the x, and let's see how this is going to help me. So I'm gonna have the 2 here, then a 2 over 2 to the x okay, and then minus x ln of 2 like that. So let's review this again. So if I distribute, I'm gonna get x to the x plus 1 minus 2x and then minus x squared to x ln of 2. This is exactly what we have. Okay. So x is greater than or equal than 2. So that means that since x is greater than or equal than 2, this term right here is positive. So this one right here is greater than 0 since x is greater than or equal than 2. Yes? Remember, exponential is always positive, so 2 to the x is always positive. And this factor here could be negative if x is negative, but x is positive. X is greater than 2. So this factor here is positive. So the sign of this expression relies entirely on this parenthesis. Okay? So I'm going to work with this parenthesis then. All right, so 2 minus 2 over 2 to the x minus x ln of 2. What can we do here? Is this positive or is this negative? So let's see. When I can certainly see that this is going to be a negative number, and I'll tell you why. When x is big enough, this is going to be negative. And the reason is because the bigger x gets, this fraction 2 over 2 to the x is going to be very small. So it's not really going to count. So we just need this term in absolute value to be bigger than 2. And that's going to happen very quickly. Okay? So, for example, this is actually equal to, let's see. This is ln of 2 to the x. I'm going to bring the x inside the ln. And let's see. When this is a 9, when 2 to the x is, so this is 2 point something the base, but let's assume that if the base was 3, okay? If the base was 3, then you just need a 9 here to already have a 2 that will cancel out with this one, okay? And then you're gonna get something negative. So what happens when x is equal to 2?
It's negative.
So when x equal to 2 is already negative?
Yeah, because ln of 2 is 1.7 something, I think, times 2. And also,
No, ln of 2 should be less than 1. It's 0 point something. Because e is bigger than 2.
0.69, but also you have the minus 1/2 on the, because 2 over 2x when it equals to 2, when x equals to 2 is 1/2.
So let's see. This let me keep the x in here.
Would it be a 9 or 4?
So I'm gonna keep the x in there, and what I'm gonna do is I'm gonna say that this term, okay, just to make things simpler, this quantity here is certainly positive, right? So if I remove it from here, I'm gonna get something smaller, because notice that I have this expression and I'm subtracting a positive quantity, right? If I remove it, I just don't want to have that 2 to the x in there. So if I remove it, I'm gonna go down, I'm gonna get something smaller. And how would that help me? If I say that something smaller is negative, that doesn't necessarily mean, no, actually, if I remove it, I'm gonna get something bigger, right? If you subtract something, you remove it, what do you get? You get something bigger because you're no longer subtracting that quantity. So here's what I'm saying. If you have a minus b, and you know that b is positive, then this is going to be smaller than a. So if I remove b, then a minus b is smaller than a. Do you understand this? That's what I'm going to do. I'm going to remove 2 over 2 to the x. I'm going to get something smaller as a result. Okay? So, actually something bigger. So this is going to be less than 2 minus x ln of 2. And that's something easier that we can manipulate, since 2 over 2 to the x is positive. Okay? So I remove this from here, and then I'm going to end up with something that's bigger because I'm no longer subtracting a positive quantity. Do you understand this? So if we show that this is negative, then our quantity has to be negative. Right? That's all we need. And the question is this negative? Well, I mean, this is a line with slope negative ln of 2. So this line is going down, right? So we know that this is going to be negative pretty soon. And let's just find the x-intercept. What's the x-intercept of this line? So this is now a line, okay? So we have the line y equals 2 minus x ln of 2. And then let's just find its x-intercept. So let's figure out when it equals 0, right? When would that quantity hit 0? So that happens at 2 over ln of 2. And what is this? So 2 divided by ln of 2.
2.885.
So that's 2.885. Okay? So this line is going down because it has a negative slope, right? The slope is negative ln of 2. It hits 0 at about 2.885. So certainly when x is 3, we're already below the x-axis, right? So if you think about the graph of this, how does it look? Here is 2, that's your y-intercept. Then over here we have this 2 over ln of 2. And remember, 3 is over here, and then this is a line that goes down. So this line looks like this. So the point is that at x equals 3, we already have a negative quantity here, and for anything bigger than 3, this is negative. Do you understand this? So for x greater than or equal than 3, this is the negative value, therefore our parenthesis is going to be negative as well. So the conclusion is for x greater than or equal than 3, we have a 2 minus ln of 2. So we have that that's negative. So 0 is going to be greater than 2 minus x ln of 2, which at the same time is greater than 2 minus this quantity. Okay? And then if this quantity, now we have that this quantity, which is the one that we have in the parentheses, is less than 0, therefore this numerator that we have here is going to be less than 0 if the first factor is positive. So x times 2 to the x times 2 minus this quantity is going to be less than 0, which implies that our derivative is less than 0 for x greater than or equal than 3. Remember, we obtain all of this inequality for x greater than or equal than 3. Okay? And just to quickly see what's going on, with two derivatives, we obtain this expression, and then our job is to figure out is this positive or is this negative. Okay? For x greater than or equal than 2. It turns out that we should consider 3 instead of 2. But that's okay, because we already know that C2 is bigger than C3. Okay? And what this is telling me is that after C3, it just keeps going down. So that's exactly what we're looking at. So we need to look at the sign of this derivative. We realize that the denominator is positive because it's being squared, so the sign really depends on the top. So we went ahead and I wrote down the top, and let's try to figure out what we can do here. So I just want to get rid of the problematic terms in here. Okay? Notice how we actually boil down this question to a line. And then once we are in a line, it's pretty easy to see what's going on. Okay? So the first thing that we did was we factored out x times 2 to the x, and you can check the algebra here, just factor that term out. And we made a note that because x is positive, okay, in particular we're analyzing x greater or equal than 2, this factor that we took out is a positive term, okay, because 2 to the x is positive. So the sign of this, which is what we want, that's a good thing about inequality, that you can put and remove stuff because you're just trying to figure out if something is positive or negative. So the sign of this depends on the sign of the parentheses. Okay? Now my parenthesis is simpler than the first expression that we have. So let's look at the parentheses instead. Again, in the parentheses, this 2 to the x that we have down here is really bothering me. I wanted to get rid of it. Why can we get rid of it? Well, because since that's positive, we're subtracting a positive quantity. If I remove it, I will get something bigger. If that stuff that's bigger I show is negative, then I am negative as well. Because if you are below something that's negative, then you have to be negative. Do you understand the reasoning? That's basically what we're doing. So remove this, and then we end up with a line, and at this point, it becomes clear what's going on. This is a line with negative slope, so it's going down. We know eventually it will be negative. We want to know when, and we know this happens right after the x-intercept. So you look for the x-intercept of a line, that's when y is equal to 0. We see that it happens at 2 over ln of 2, which is about 2.885. In other words, when x is 3, we for sure we're going to be under the x-axis. Okay, and from now on, it's going to stay below the x-axis. So this quantity 2 minus x ln of 2 is negative. Therefore, the other quantity with the 2 over 2 to the x is also negative because it's smaller, which then means that this parenthesis was negative, making this expression up here negative, which was the numerator of a derivative, and therefore a derivative is negative. Okay? Again, inequalities are not like equations. Equations you solve in one way, you're solving. Inequalities, you need to play with different ideas. Okay? That's why I'm saying if you can do the simple algebra like the previous one, it's easier. But sometimes it's not that straightforward and you have to do some computations. Okay? The point is that we figured out that for x greater or equal than 3, the function is decreasing. So the sequence Cn is monotonic. And we get a strict inequality, so it's monotonic decreasing. And I'm going to say for n greater or equal than 2. So we know for sure this argument shows that it's monotonic decreasing for n greater or equal than 3. But by our calculations above, when we computed the terms, we saw, so what we know is now that from 3 on it keeps going down. Okay, this is what we just argued, that this keeps happening. Okay, but we know also that C2 is bigger, so we can stick it in and then say for n greater or equal than 2. So really, this term is the one that is not behaving the way it should be, right? Because after the first term, everybody else is going down. So technically, you just ignore it and move on with your life. Okay, that's basically what we do in that situation. Okay, questions about this example? Yes.
So Professor, I'm just a little confused where you remove the little thing, like the very tiny number. I'm like, I got because it's very tiny, we can remove it and it'll stay positive. But then you wrote something like there that I didn't really.
What did I write?
No, I mean, you wrote that this is bigger because we removed it or something.
Of course.
I don't understand.
It's smaller.
Smaller.
So we get something. So I'm removing a positive quantity that you're subtracting.
A very small one.
It
doesn't matter.
Actually, it doesn't matter whether it's more or not. The point is that it's positive, and we are subtracting that positive number. You see how it has a minus in front?
Yeah.
So we're subtracting that positive thing. If I remove it, what do you get? Something bigger or smaller? Think about
Bigger.
it. Remove it, you get something bigger. That's all I did.
Okay.
That's all I did. Right? So you have 3 minus 2. If I get rid of 2, I get something big. I get 3.
Okay.
Right? That's all I did. All right. Are we good? I mean, it's okay. You're not playing with inequalities, then this looks like magic. But it's not really magic, right? When you look at it. The question is, what's bothering me? Okay, this term is bothering me. Can I remove it and then still get what I want? Yes, remove it. Okay, you just need to justify. The beauty is this, that we're doing inequality. Now, if this was an equation, that's a different story. You cannot remove stuff. You know, but we're playing with inequalities. That's all. You don't like it, take it away. All right, so that was that one. And then how about this one? Arctangent. So the n is going to be arctangent of n. So, for example, here calculus is a one-shot answer, right? So if we consider, and here we can say for n greater than or equal than 0. Here, if we consider f of x, what is this? So if we consider f of x equals arctangent, then what's the derivative?
1 over x squared plus
1 over 1 plus x squared. And what do you know about this? It's always positive. Remember, you don't care about whether this is increasing or decreasing. The derivative you don't care about is monotony. What you care about is the sign of the derivative. Okay? The sign of the derivative tells you what happens to the monotony of the original function. Okay? The monotony of the derivative tells you the information about the concavity of the function, but we're not talking about concavity here. Okay? We just want to know whether our function is going up or down, and the derivative will tell you that. In this case, this is always positive because you have the x squared in there, right? 1 plus x squared. So it's always positive. So what does that mean about our sequence? So our sequence is monotonic, increasing. Okay? All right, questions?
It says n bigger or equal than 0? Or?
Yeah, because this is sequence, so I have to tell you, you know, what do I mean by n? So let's start at 0. Eh?
So it's sort of like the bounds of the sequence.
Not the bounds. It's n is the subscript.
Like, where it starts.
You know, D0, D1, D2, D3, and so on. The n. So if I ask you now, what's the fifth term of the sequence? Let's see, what's the fifth term of the sequence? Arctangent of what?
No,
6.
Of 4.
Because
We are starting at 0. If you are a computer scientist, then you are used to that. If you are not, then you have to get your head around that, because usually you start counting at 1, but here we're starting at 0, right? We're counting starting at 0. So if I ask you for the fifth term, that's really n equals 4. Now, if n started at 1, then the fifth term is n equals 5. Do you understand this? Okay. So all I'm telling you is where to start. Okay. I want to start at 0, so that the first term is 0. Arctangent of 0, which is 0, right? And then arctangent of 1, arctangent of 2, etc. Okay. All right. So that's the monotony of a sequence. Now, why do we even care about this? Why is this relevant? Other than, remember, a sequence is just a list of elements. Okay. At least this is a way of putting a name to this behavior of either the terms are going up or down. But why is this helpful with convergence, for example? We need to pair this with something else. For example, the notion of being bounded. A sequence is bounded. Bounded means that there is a certain point that it cannot go beyond or below that point. So it's between two numbers. But all the terms of your sequence are always between two numbers. Okay? That's what we mean by a bounded sequence. And the one above, we call it an upper bound. So we say the sequence is going up and it has an upper bound, we say it's bounded above, and the one below is a lower bound. Okay, so I'm going to define all of these terms. So definition. This is the definition of bounded sequence.
Can we solve this one by the definition of the domain and range of arctangent?
So a sequence AN is bounded above if there is a real number m, such that For all n, we have the following. We have that an is less than or equal than this number n. So basically, what I'm saying here is a sequence bounded above means that there is a number for which none of the terms in our sequence will go beyond that number. Okay? This number, we call it an upper bound. So m is called an upper bound. For the sequence. Okay? Yes?
So would this be like, in the instance of rectangle, would it just be like power 2?
Power 2 would be an upper bound, good, but it's actually a special one. That one is called the least upper bound.
Oh, because then it's also, okay.
Because that's the smallest such upper bound that you can have, because your term, the sequence is actually approaching that number. Like, if you go a little bit tiny below pi over 2, you're gonna get into that little distance with your sequence, because the limit is pi over 2, right? So, good.
It will never actually reach power.
But that's actually an axiom of the real numbers. That if you have a sequence of real numbers, and this sequence is bounded above, if it has an upper bound, then there is a least upper bound. But there is a number that's an upper bound, and it's the smallest. So what does that mean? If you go a tiny bit below that number, you will find elements in the sequence in between. So that means you cannot really go beyond that. You cannot go below that, okay? So, but that's an axiom. That's called the existence of the least upper bound. Yes?
What does that say? The sequence an is bounded above if there is a real number m? What does that
Such that.
Oh, such that.
Okay. Such that for all n, an is less than or equal than m. M is called an upper bound for the sequence, and here is this is really an axiom. Slash, this is actually follows from the completeness. This is the completeness of the real numbers. The completeness of the real numbers, which basically says that when this happens, then there is a least upper bound. So the smallest such m is called least upper bound, and we usually abbreviated by LUB. So the smallest such m is called least upper bound, and it exists for real, and it exists if our sequence is bounded above. Okay, so if you do have a sequence that's bounded above, then you know that there will be a least upper bound. It turns out that that least upper bound is actually the limit. Okay, the sequence has to be increasing. That's the theorem that we're about to write down. Okay, so that's the definition of what it means to be bounded above and the notion of upper bound. Okay, yes.
So the number that's the least upper bound and the upper bound are different.
Yes, actually, how many? Let's say that you have a sequence that is bounded above, and let's say that it's bounded by m.
Okay.
How many upper bounds does it have?
It depends on the function.
You already know that it's bounded above. It's bounded by m, where m is whatever number you want. How many upper bounds does it have?
One.
An upper bound is something that it can never pass, right?
So infinite.
Right. Oh, right. Because if the upper bound is 2, then it also can't pass 3.
Yeah.
4,
Okay.
5.
So then 2
So
isn't.
if m is an upper bound,
but it's the least upper bound. So it's the
well,
lowest.
no, I didn't say least.
Okay.
Maybe there is a smaller one. But if m is an upper bound, then m plus 1, m plus 2, m plus 3, and anything bigger than m is an upper bound as well, right? So if a sequence is bounded above, it automatically has infinitely many upper bounds. Okay? It has infinitely many upper bounds. Now, the point is that there is one that's the smallest.
Right.
And that's the one that we usually interested in, because that will be the limit if the sequence happens to be increased.
Right.
If it happens to be increased, okay, then and we call it the least upper bound. Okay. All right. So least upper bound, there's only one. That's something that you can think about. If it has a least upper bound, there has to be just one. You cannot have more than one. Okay, now similarly, we have the notion of bounded below. Okay, the sequence is bounded below. You know, if there is a number for which the terms of the sequence never go below that number. Right? So a sequence an is bounded below if there is, I'm gonna say an n, if there is a real number n, if there is a real number n such that for all little n, the terms in our sequence an are actually greater than or equal than this fixed number n. Okay. In other words, bounded below means that there is a number that there is a floor for a sequence. There is a place for which the terms of our sequence do not go below that value. Okay, and this number n is called a lower bound.
Is this for only monotonic sequences?
No, not necessarily. We're gonna see examples now.
Oh, so like
now a theorem says that if you have a sequence that's monotonic and bounded, okay, then it must converge. That's why we're looking at these things, because now if you have a sequence and you can show that it's monotonic and you can show that it's bounded, maybe you cannot find the limit, but if you show these two properties, then you know there is a limit. You know it converges. That's
oh, so like
just think about it. Imagine, think about a tangent. You know a tangent is bounded above by pi over 2, for sure. And moreover, you know that it's always increasing, because we just showed that it was always increasing. The terms are always going up. So it's always going up, going up, going up, but it cannot go beyond pi over 2. It has to get close to something.
So it gets close to pi over 2.
Well, that you need to prove it. But then, of course, we know it because of the graph and so on. But the point is that we know that if something is going up non-stop and is bounded above, it has to hit something, it has to get close to something. Okay? And that something is what we call the least upper bound. Okay?
Would we prove it by doing the limit of?
You need to use an epsilon delta argument, because basically you said, okay, the claim is that it doesn't go below the beyond the least upper bound. I mean, that's by definition, because it's bounded, there is a least upper bound. Now, we claim that that's a limit. How do you show that's a limit? You need to show that the terms of the sequence are arbitrarily close to the least upper bound. What do? Take an epsilon, a very positive, small positive number, and consider L, which is the least upper bound, minus epsilon. Okay? That's another number that's less than the least upper bound. Because it's not an upper bound, because then it would be the least upper bound, because it's smaller than the least upper bound, right? Because it's not an upper bound, there has to be terms of your sequence that go beyond that number. So that's it. So you know that and if that term is beyond that number, then infinitely many terms in the sequence are in there, because the sequence is increasing. Anything that's bigger than that is in that tiny little piece. So I guess if I show you a picture, it's easy. So you have a sequence that's going up, right? And you know it's bounded above, so you know that it cannot go beyond a certain point. Over here is your m. That will be your upper bound. Okay, it cannot go beyond that. There is a least upper bound somewhere. Okay, because that's an axiom of the real numbers. So I claim that that's the limit. So I'm gonna put it here, L, which would be the least upper bound. So that means that my sequence is not gonna go beyond this. Okay, I claim that that will be the limit of the sequence, assuming that the sequence is always going on. How do we do that? Well, just move a tiny bit, because being a limit means, remember the definition, that for every epsilon there exists an n, such that for every time in the sequence after that point on, the distance between the sequence and your L is less than that epsilon. Okay? So pick whatever positive number you want. So just move a tiny little bit. Let's call this L minus epsilon. Okay? Notice that this little epsilon is as small as you want. You can make it smaller and smaller, and the same argument is going to work. Okay? Now, two things to have. Either the terms of our sequence stay below the blue line, or they go beyond the blue line at some point, and then everybody after that is in this little strip. They cannot go beyond the red, because by definition this is an upper bound, right? But they could go beyond the blue. If they don't, then that means that the blue will be an upper bound. But what's the problem with that?
You don't know if it's the least upper bound.
No, we said that this was the least upper bound. So that would violate the fact that this is the least upper bound. So this is impossible. They have to go beyond because there's only one least over bound. And we declared that this was the least over bound. Okay? So because L is the least over bound, that means that eventually the terms of my sequence, they're gonna cross this blue line, right? And then these guys, these are just finitely many terms. They don't care. You can just ignore them. And starting from this point on, all the terms in my sequence, they are in there. And they are infinitely many, right? And that's what the definition of limit says. That starting at some point, by going deeper into a sequence, eventually, all the terms are a distance less than epsilon from the value that you claim the limit. And you can play this game for whatever epsilon you give. You know, there will be a blue line, and your sequence has to go past that blue line. Okay? So that's the theorem, that if you have a sequence that's monotonic and bounded, then it converges. This, we did it, bounded above and increasing. Then similarly, there's a similar argument if the sequence is bounded below and it's decreasing. Okay? Because remember, monotonic has to be either going up or down, one of the two. Then bounded means that it's either above, that is both, above and below. So you have a sequence that's bounded above and below, then you know that is, and it's monotonic, it will converge. Either to the least over bound or the greatest lower bound. Because I was about to define this. So n is called the lower bound, and again, the bigger such n is called the greatest lower bound, GL or GLB. So n is called a lower bound. I'm gonna keep that in there. But all of this that I do with the picture and talking, we actually write in symbols, right? That's called an epsilon delta proof, what I just talked about here. Which you should have seen in Cow 1 at least once, to have an idea of what this is. Because that's how you actually argue limits of functions. Why does the limit of x squared as x approaches 2 equals 4? How do you prove that? You have to do your epsilon delta in there. Okay, so n is called a lower bound, and the greatest such n is called greatest lower bound. And we abbreviate this by GLB. Okay? And the point is, just like for the least over bound exists, this one also exists. Okay? If a sequence is bounded below, it has a greatest lower bound. Okay? In there, and the logic is the same. Okay, so number 3. Now we know what it means to be bounded above. We know what it means to be bounded below, and what it means to have a lower bound. So we say a sequence is bounded if it's both bounded above and below. Okay? So a sequence is bounded if it is both bounded above and below. Okay? And if you want, what that means is that there is an m such that for all n, the absolute value of an is less than or equal than m. Remember that this means that the terms of your sequence are between m and minus m. That's what I'm saying when I put the absolute value. So, you know, m is an upper bound and negative m would be a lower bound, right? So sequence bound.
They don't have to be the same number.
You can actually make it so that this number is always the same, because just let m be the maximum of the two.
Oh, okay. Is that what we're going to be?
No, that's if you're going to write a formal argument.
Okay.
That's what you would do. It has an upper bound, it has a lower bound. You look at the absolute values, take the maximum, whichever has the greatest absolute value, and that's what you call m in this definition. You can always make it like that. In fact, I'm going to ask you a question. Can you argue that if a sequence is increasing, then it's bounded? Let's say that you have an increasing sequence that's bounded above. How would you argue that it's bounded? No, you already know it's bounded above. How do you argue that the sequence is bounded? Remember, bounded means both.
Oh,
you have to be bounded above and below. So you need to argue that it's bounded below now.
Take the limit as it approaches negative infinity.
It's in, what does that mean? Remember, sequences, they start at 0 or 1, right? Sequence is just a list.
Oh, so you find.
So you find the first term? No, I take the limit to 0, right?
Sequences are not functions. You can only talk about limit and infinity.
Okay.
Sequences are not functions. But you're more or less on the right track. Look, just look at this picture. If the sequence is bounded above, that means that all your terms are less than a number, right? To find where it's bounded, that is bounded below, and it's increasing, that's important. If the sequence is increasing, actually, that's it. The first term does the job, right? If the sequence is increasing, that means that everybody else is bigger than that first term. So the first term is your lower bound. Do you understand what I'm saying?
Yeah.
If the sequence is increasing, the first term is your lower bound, or anything below that term, for that matter. Okay, so that was not so much of a clever question. I mean, it's interesting, and we're gonna use that idea actually. Anyways, do you understand what it means to be bounded? Okay, so now the theorem is that if we mix the two together, we get convergence. So if you have a monotonic sequence that's bounded, then it must converge. Okay? So theorem, this is called the monotone convergence theorem. And to prove it, you need the existence. I mean, what I sketch here is a proof of the monotone convergence theorem for the increasing case. Then you have to do a similar argument for the decreasing case, but it's the same idea. Okay. So this is called the monotone convergence theorem. And basically, what it says is that a sequence that is monotonic. Remember, monotonic could be increasing or decreasing, one of the two, okay? That is monotonic and bounded converges. Okay? If it's increasing, then it converges to the least upper bound. If it's decreasing, it will converge to the greatest lower bound. Okay? So let me actually stress that. So if it is increasing or non-decreasing, okay? I'm just gonna write increasing, but also non-decreasing. If it is increasing, then it converges to its least upper bound. If it is decreasing, then it converges to its greatest lower bound. Okay, so that's the monotone convergence theorem. All right, so let's do some examples, and then we're gonna close this section with the exercise that I asked you to think about last time, with the one with the nested square roots. Which I kind of gave you away the idea of how to find the limit, but all of that little trick assume that the limit exists. So you first need to argue that the limit exists, and this is what we're going to use, the monotone convergence theorem. So we have to show monotonicity and boundedness for that sequence. And once we do that, then we're good to go. Okay, so examples. Let's say an. Let's say this is the sequence 1 over n. So this sequence, let's say, is this monotonic? Is monotonic? Monotonic what?
Decreasing.
So this is monotonic. And in this case, we can say decreasing, right? Monotonic decreasing. Is it bounded?
Yes. No, it's not bounded.
What do you mean it's not bounded? It's between 1 and 0. The terms here never get above 1, and they will never get below 0.
Yeah.
Right? This is bounded. So it's monotonic and bounded. So for the bounded part, notice that 1 over n is always greater than 0 and less than or equal than 1. So if you want, you can take your m to be 1 in the definition above. That's okay. It's bounded above by 1, it's bounded below by 0. It's bounded. So it's bounded, it's monotonic, it must converge. Indeed, we know. What does it converge to? To 0. And 0 happens to be the greatest lower bound. Because anything above 0, you can find an n that's going to make it low. Okay? Give me any number that's bigger than 0, I can find terms in my sequence that are less than that number that you give by making n big enough. Okay, so it converges. And indeed, we know it converges, right? It converges to 0. Let's see, and another one. I want you to understand that a sequence could converge and not have these properties. Okay. So what this is saying is that if it is monotonic and bounded, then it converges. But if a sequence converges, doesn't mean that it has to exhibit this behavior. Okay. So just keep that in mind. So how about this one? What do we know about this? Is this monotonic?
Yes.
We analyzed that before, right? The terms were getting bigger and bigger. This is the one that we did with algebra. So this is monotonic increasing. Is it bounded? What's the limit of this? The limit of this is infinity because you know the top is a square and the bottom is 1. So this is monotonic, but it's not bounded, and that's the reason why it actually doesn't converge. It diverges, right? Because it's not bounded. If it's monotonic, for that to converge, it better be bounded. Okay. If it has one of the properties and converges, it has to have the other. So it's monotonic increasing, but it's not bounded. So the point of this little example is just to let you know that if you want to guarantee convergence, you need to have both. Having one of the properties is not enough. Okay? If it's increasing but it's not bounded, that means it just keep going up non-stop. So it's not going to converge. It's not going to get close to anything. And for example, how about this silly sequence? The sequence -1 to the n. Is this sequence monotonic?
No.
It's not monotonic because it's oscillating between 1, -1, 1, -1, 1, -1, right? This is like our 3 and 1 sequence, right?
But it does get bounded.
Very good, but it's bounded. But does it converge? No. It doesn't converge. So you see, having one of the two properties is not enough. It's just when you combine the two properties, then you force the sequence to converge. So this is not monotonic. But it is bounded, right? -1 to the n is always between 1 and -1. In fact, it's one of the two all the time, right? It's bounded, but it diverges. I put here this one, and it diverges, and it diverges. Okay? Yes?
With that being said, that if it's monotonic but not bounded, is it always divergent? Or does it always diverge? Or are there cases where it does diverge even when it's not bounded, but it is monotonic?
So if you already know that it's monotonic, let's say, because then you need to know it's either increasing or decreasing, it's one of the two. Let's say increasing. You know it's monotonic increasing, and you're telling me it's not bounded. That means in particular it's not bounded above. So that means my terms are just going to keep getting bigger and bigger and bigger non-stop.
Okay.
So it's going to diverge. If you have one of the properties but not the other, then it cannot converge. Now it could be that you have a weird sequence that doesn't exhibit any of the two properties and still converges. I cannot think of an example right now. I don't want to say that it doesn't exist. Yeah, I don't want to say it's not possible. But if it has one of the property, if you want convergence, you better have the other. Okay. So let's see. Yeah, exactly. Because for example, if it's bounded but then it fails to be monotonic, what can the limit be? Because if it's not monotonic, it means your terms you have no control of the terms. So it's not gonna get close to anything. No. Have to be careful. You see, here is a counterexample. What if the sequence of absolute value goes to 0? So it could be bounded. Just imagine, look at this picture. Here is 1, here is -1, and then you have a sequence that does this. You know, like negative 1, like negative 1 to the n over n. Look at the sequence. That sequence is always in absolute value between 1 and negative. I mean, it's never beyond 1 and it's never below negative 1. It never is going to happen. And it's not monotonic because, you know, it's positive, then negative, because of the negative 1 to the n. But as n goes to infinity, then it's going to go to 0. We saw that theorem last time. You can use quiz theorem on this, right? Yeah. Negative 1 over n below, 1 over n above. It goes to 0, so it has to go to 0. So it converges. It is bounded, right? But it's not monotonic. So it could be bounded and converge without being monotonic. But the other way around, no. If it's monotonic, then it better be bounded if you want it to converge. Okay. So that's yeah. So you see.
Yeah. Could you repeat that part? So if it's monotonic, it better be bounded to converge.
To converge, because just think about it. If it's not bounded, if it's monotonic, let's say monotonic increasing, it means that it's just gonna keep going up non-stop, right?
So there's no like limit it's gonna reach.
Exactly.
If it keeps going up.
So there is no way it can converge. But what we just said here is that it could fail to be monotonic, but if it's bounded, it's possible for it to converge. Here is an example. Okay. Now, it could be that this is. Okay, I don't want to. Yeah, because now, you know, I want to say just in this case, but no, because if I now say +1, I'm basically just translating this situation, and then, you know, between 0 and 2, and it is 1, so you can place this whatever you want.
I'm sorry, Professor, so here there's no like least upper like limits, right? Or boundary, yeah.
Because it's not monotonic. Remember, it has to be monotonic
for it to have a least.
For it.
And the greatest.
So
it's just
no. Sorry. There is a least upper bound. The least upper bound is 1.
As 1, it's the same as the upper bound. The upper bound.
Well, but 2 is also an upper bound.
Okay.
3 is an upper bound.
So they're all upper bounds, but what it like actually reaches is the least upper bound.
Sometimes it doesn't reach.
Almost reaches.
Yeah. For example, our tangent never reaches pi over 2.
Yeah.
Because that's a horizontal asymptote. But that's the least upper bound. So sometimes the least upper bound is part of the sequence, right? Sometimes it's not.
Sine of x.
Sine of x, 1 would be the least upper bound, right? So, okay, good. So let's close this discussion. We have talked too much about sequences. Let's close this with the square root question. So another example. Determine the convergence of the following sequence. So the sequence is the sequence AN. Actually, I'm not going to give it a name yet. It's going to be square root of 3, the square root of 3, square root of 3, square root of 3, or the square root of 3, square root of 3, and so on. You understand what the sequence is doing, right? It's just 1 to square roots, square root of 3, one nested inside the other. So the question is, would this sequence converge or not? Okay. All right. So to analyze this, let's try to see if we can argue whether this is monotonic, okay, and if it's bound. Okay. If we get monotonicity and boundedness, then it better converge. So it will have a limit. Okay. I think it should be clear to you. We're gonna argue formally anyways, but it should be clear to you that this is an increasing sequence, right? Because we're basically making the stuff inside the radical bigger at each step. Just multiplying by a number that's bigger than 1, so that the inside the radical is getting bigger. So the whole radical is also getting bigger. But let's formally justify this. If we call this A1, and this one we call it A2, if this one we call it A3, and so on, what do we notice? So note, hopefully you realize that A2 is actually equal to the square root of 3 times A1. Right. And similarly, A3 is the square root of 3 times A2. Yes? In other words, the nth term of the sequence is given by 3 times an minus 1. So all you have to do is, by the square root of 3 times the previous term, right? Because basically what you're doing is sticking an extra square root of 3, right? So we have this recursive behavior, so we can actually define the sequence as follows. We can say that the first term is square root of 3, and then any other term can be calculated by doing the square root of 3 times the previous term, as long as n is 2 or bigger. Okay? So this is a recursive definition. I'm going to take advantage of this recursive definition to show these properties that we want on monotonicity and boundedness. Okay? So first, an is monotonic. Let's argue this. Okay, so I'm going to compare this with 3. So note a1, which is equal to square root of 3, is certainly less than 3, right? Agree?
Mm-hmm.
Okay. Do I want to compare it with 3? Yes. So that means if I multiply this by 3, so 3 times a1, that's going to be less than 9, right?
Mm-hmm.
If I multiply both sides by 3, I get that 3 times a1 is less than 9, and if I take square root, that's again less than 3. Do you understand this? But what is square root of 3 times a1? That's a2. So we get that a1 is less than 3, but a2 is also less than 3. I actually want to argue that everybody is actually less than 3 anytime in this sequence. Okay. So by doing this, to do this, I'm going to use something that's called mathematical induction. Did you study this back in pre-calculus? Okay, so mathematical induction is actually pretty straightforward. It's an axiom. Have you ever played? You know what dominoes are, right? So if you place, let's say that I place infinitely many dominoes. Let's say that you have an infinite amount of dominoes pieces, and you place it in such a way that they are a distance from each other that if one falls, it's going to hit the next one and it's going to make it fall. Do you understand the scenario that I'm talking about? A bunch of dominoes pieces going to infinitely many dominoes pieces. In such a way that if one falls, it's going to hit the next one, that then it's going to hit the next one and so on. So what happens if I hit the first domino piece?
A never-ending stream of dominoes falling.
Yeah.
So do you agree that no matter what domino piece you look at, eventually the piece is going to fall?
Yeah.
So we can say that they will all fall. Now, you're not going to be there to see. There are infinitely many. Eventually we die and the domino pieces keep falling. There are infinitely many, right? And the finite amount of time that we're alive. However, you can argue that no matter what domino piece you look at in that infinite string, eventually would be turned to fall down. Agree? That's what the induction principle says. Basically, it says you have a mathematical property that is true, let's say, for 1, for n equals 1. And then if you argue that if it's true for k, then it's true for k plus 1. So if it's true for a number, it must be true for the next one. When you put these two together, the basic condition is it works for 1. Now, I know that if it works for a number, it has to work for the next one. You put those two together, it means that it's going to work for everybody. Because if it works for 1, then it has to work for 2. But if it works for 2, then it has to work for 3. And so on and so forth, and then it's going to work for another numbers. Do you understand this? So that's what I'm about to do here. So when n is equal to 1, my term is less than 3. I just did this now to reinsure this. When n is equal to 2, I also get that it's less than 3. Now I'm going to try to argue that no matter what n is, it will be less than 3, so I'm going to use induction. So what you do, assume that it works for k, and using that, can we show that it has to work for the next one? Just like we did here. You see, it worked for 1, and we showed that it has to work for 2. So this kind of already gives you the technique that we're going to do. Okay? So that's called induction. Now, using induction n, we have the following. So for n equals 1, this is called the base case. Okay, let me do it a little bit more formally. By the way, if you know programming and you are into computer science, something similar to induction is recursivity. When you define a recursive formula, you need to have a base case. Because otherwise, you're gonna have your program is gonna be in an infinite loop and it will never stop. Okay, you need to tell the program when to stop. For example, how do you define the factorial function recursively? So we talked about factorial last time. Remember, factorial equals n times n minus 1 times n minus 2 and so on, all the way down to 1, right? So if you wanted to define a factorial function, how can you define it recursively? Recursive means using the same function to define itself. You can say, well, this is n times n minus 1 factorial. But if the computer only does this, eventually, it keeps doing into this n minus 1, then this n minus 1 times n minus 2 factorial, then n minus 3 factorial. Keeps doing that, eventually it needs to stop. So when you do your program, it will look something like this, depending on the, on the computer language that you're using. But let's say that the output is going to be an integer, and it's going to take an integer. Okay, let's call it a, and then you need to say, well, if here is our stopping condition, if a is equal to 0 or 1, but we want to be able to do 0 factorial. So if a is equal to 0, then we're going to return 1, because the factorial of 0 by definition is 1. Otherwise, so if this condition is not satisfied, meaning if you give me here a number that's bigger than 0, it's going to ignore this if, and then it's going to execute the next line. All you have to do is return the result of doing a times factorial of a minus 1. That's it. That's your code. And what's going to happen is that now when the computer is running this code, okay, it knows that it has to return a times something. Now it's going to put this on a stack. There's a data structure called the stack. Sometimes when you get an infinite loop, what happens is you get an error that says stack overflow, meaning that you run out of memory in your computer because you have a bunch of stuff in there and it was not able to get rid of it. Okay, that's what stack overflow means. So it's going to place A on the stack and say, okay, I'm going to use you later. I know I need to multiply you by whatever this is. But then it's going to go and compute this. Now, when it computes factorial of a minus 1, it comes back and executes this code again. But instead of a, there is an a minus 1 as an input. It has a question. No, it's not 0. Okay, then I go here, do this, bring it to the stack, the a minus 1, and then it has to compute a minus 2. If we don't put this stopping condition, eventually this is going to hit 0 if we're doing minus 1, minus 1, minus 1, right? If you don't put this stopping condition, it's going to get into the negatives. And then it's just going to keep doing that forever and ever. You run out of memory because there's no more place to put numbers in the memory of your computer. You have finite memory, and your code doesn't execute. This is called the base case, or your stopping condition in recursivity. In induction, this is the base case. It's equivalent to this. Okay? So we need to say that it works for at least something. Okay? You have to make sure that whatever you're trying to prove, it works for something concrete. Okay? Here you're defining factorial, it works for 0. Factorial of 0 is 1. Now, once we know this, you can define factorial recursively. Factorial of n is n times the factorial of n minus 1. Just keep doing this, and then eventually. Okay, so put this aside. Using induction n, so the base case will be for n equals 1, and basically it's a1, which is square root of 3, and this is certainly less than 3. Okay, so the statement means that an is going to be less than 3 for all n. That's what we're trying to prove. Okay, so a1 is less than 3. So now the second step, the second part is called inductive hypothesis. So inductive hypothesis, or inductive step. Let me call it inductive step. Hypothesis is too fancy, but that's the actual name. So inductive step, what you do is assume that AK is less than 3, okay, for K greater than or equal than 1. So this is not an empty statement. We already verified for 1. So when K is 1, this is a valid assumption, okay? Assume that it works for K, where K is at least 1, okay? Now I want to show that it's going to work for K plus 1, okay? So I'm going to put in red what I need. I need to argue, so I need to show that AK plus 1 is also less than 3, okay? That's what we need to show. If we manage to show what I wrote in red, then we're in business. Because it works for 1, and then when you couple these statements together, it means they have to work for 2, then for 3, then for 4. The 4 is going to work for another. So I need to show that ak plus 1 is less than 3. So indeed, we're going to do exactly what I just did here. Okay? So ak, we know ak is less than 3. So if I multiply by 3, it's going to be less than 9. If I take square root, it's going to be less than 3. Yes? But now, what is the square root of 3 times ak? That's exactly the next term is in our sequence. Remember, that's how we define the sequence, right? So to get a term, what we do is square root of 3 times the previous term, right? Do you understand this? Yeah. So if this is k, notice that this n really is plus 1, this one, right? If this is k, then this will be k plus 1, right? So this is exactly the next term, ak plus 1. So we have that ak plus 1 is less than 3. So by induction, you do this more formally in discrete math, that's when you learn this, but you also choose it in pre-calculus, okay? So by induction, it follows that an, the sequence an is less than 3 for all n greater than or equal to 1. Okay? All right. So what this is telling me is that this sequence is bounded. Okay? It's bounded above by 3. I said I was going to show monotonicity, and that's not what it did. So I would say it's bounded. To show monotonicity, I need to compare one term with another. Okay, so actually this was the hardest part. So we showed that it's bounded, so it's bounded above by 3, and therefore once we put it with monotonic, it's going to be bounded below by the square root of 3. But right now we can say it's bounded below by 0 because the terms are all positive, right? So it's bounded below by 0 and bounded above by 3. So an is bounded above by 3. Okay, so number 2, monotonic. So again, we have that an, so a1 is equal to square root of 3, and then an is going to be the square root of 3 times an minus 1. So I want to argue that the next term is always bigger than the previous term, okay? That is increasing. So how do we do that?
And you prove that since the square root of 3 is greater than 1, you will always be multiplying by something greater than 1.
Yes.
So then it would always be great. The next term would always be greater
But
than 1.
no, because you're not multiplying by square root of 3. So let's see. So note, let me write it down here. So the square root of 3 is less than the square root of 3 times square root of 3. I guess just to make it clear, 3 is less than 3 times square root of 3. Since square root of 3 is bigger than 1, right? So you multiply a number bigger than 1 by something, then you make it bigger. So now if I take square roots, still holds. So this is a1, and this is a2. So a1 is less than a2. And actually I'm going to play the same game now. I want to show that by induction, that if you know that that ak, so a1 is less than a2, then the statement that I want to say is that ak is less than ak plus 1. Okay? So assume that ak minus 1 is less than ak, okay, or ok greater than or equal than 2. Because you see, when k is 2, then this is a 1, and we have that extended. That's our base case. We know a1 is less than a2. Okay? Assume that ak minus 1 is less than ak. And what I want to show is that then, assuming this, then I can argue that ak will be less than ak plus 1. Okay? Because then that would tell me that because a1 is less than a2, then a2 will be less than a3. But then a3 will be less than a4, and so on. And then the induction kicks in. So assume that ak minus 1 is less than ak for ok greater than or equal than 2. So what do I want? I want to show that ak is less than ak plus 1. Let's see if we can do that. Okay, so we begin what we have. So we have that ak minus 1 is less than ak. I'm going to multiply this by 3. So inequality still holds. And then it takes square roots. The inequality still holds. What is this term equal to? What's the square root of 3 times ak minus 1?
AK plus 1.
That's ak. That's the next term, which is ak, right? This is the k minus 1 term. The next one is the k term. What comes after k minus 1? After k. So ak, right? So what is this? The k plus 1 term. So there you go. ak is less than ak plus 1. Okay? All right. So by induction, it follows that an is going to be less than an plus 1 for all n. Hence, the sequence is monotonic increasing. Okay, so we know it's bounded. Okay, so we know it's bounded above by 3. It's monotonic increasing. It has to converge. And we showed last time that it has a limit, and we showed last time that the limit is actually 3, right? We're doing the 3. So it's monotonic increasing. So the sequence is monotonic, unbounded, and so it converges. Okay? And now you know the story. So that means that your sequence has to converge to some limit L. So how do you find this limit? Well, you know that an is the square root of 3 times an minus 1. And the key observation is that if the sequence an converges to L, then the sequence an minus 1 is also converging to L. Because it's the same sequence, just one step behind. Okay? When you take the limit as n approaches infinity, then you will get L is equal to the square root of 3 times L, and then you solve for it. Okay? L squared is 3L. So you get L times L minus 3 is equal to 0. So there are two choices. It's either 0 or 3. You know it doesn't make sense because the terms there are all bigger than 0. So the sequence converges to 3. Okay? This trick you use it with almost any sequence that's defined like this recursively with a bunch of nested radicals, etc. You can play this trick. Okay? But the reason why this trick works is because first you need to know that such a limit exists. But for that, you have to go through what we did above. Okay, so we said more than enough for sequences, so I guess next time we begin talking about series.